Happy to be here. So I recognize many faces. Congratulations on your center or your institute or your program. This is the topic which I think is for the next 100 years. So it's just getting started. So I have quite a bit to say about it. I've been thinking about it, working on this area for probably a couple of decades, but certainly 10 years. And I have an hour-long talk, which I'm going to try to go kind of quickly through and pick out some things, because I couldn't think of anything to throw away. And already some of the points I'd like to make have already been made by speakers, so I'd like to pick up on some of them. So I may just kind of talk quickly and also skip over a few things, but I hope you'll forgive me for that. There's not that much that's new, really. I think new things will emerge, but there's a lot of hype, and there's way too much hype. It's uncorrelated with what's really new. There's a lot of challenges. We haven't really solved a lot of things. But statistics and computer science are 100-year-old disciplines that have already done a lot of things, and we're kind of putting them together in new ways. But there's not a lot new, but the challenges that are arising are new, and we better come up with some new ideas to face them. So just briefly, what to me is new is there's not much new in the space of algorithms. It's really just that we have not just large data sets, but a new kind of data set, and I like to think of them as individualized. We have data now not about just the aggregate, but about individuals. So in the social sphere, that's kind of revolutionary in social science, there's data about every individual. So, Amazon, Facebook, et cetera, have data about every individual. And the inferential problems that you're trying to solve now aren't general laws about human beings or about populations. They're specific laws about specific groups of people, or even specific individuals. It's true in astronomy too. I see Alex here. It used to be that you just get a telescope, you point to the sky, you try to find general laws. Now you try to find specific laws about specific pieces of the sky. And in genomics, we now know something about every gene. We have data on every gene. So you want to infer things specific to specific genes. That didn't used to be the case. So that's what's new to me. And in Silicon Valley, you hear about personalized services. And that's exactly the same thing. You have now data about every individual. You can make it different for each individual. But of course, you have all kinds of challenges, including long tails and many others. But providing timely, trustable, transparent inference and decision-making at the level of individuals, every one of those words sounds like a good desideratum. We don't know how to do any of them. Okay? So I think what's required is not just algorithms and libraries and so on. That's all important and good. That's what many people focus on. But a thinking style, which blends statistics and computer science, or more broadly speaking, inferential and computational thinking. I'm going to try to make that a little more clear as we go. Inferential thinking, I'm glad that Renee did mention statistics. It sometimes drops off the ship. It's really, to me, the core of this enterprise. It's really where it all starts. It's a 300-year-old discipline, and many of the important ideas we all use are being rediscovered, have already been sitting in statistics for quite some time. But statistics came before computer science. There was no computers. So the algorithmic side of it was fairly informal. And so bringing that more formal algorithmic side into statistics is, to me, many of the big challenges inhere exactly there. So I'm going to make this clear with a little bit of an anecdote that I've been using this for several years. I think this slide says 2015. But just to try to make this a little more pungent. So imagine a student who's gone down to Silicon Valley or wherever, and the boss says, I need you to build a big data system that will replace our classic service with a personalized service. So this happens all the time in Silicon Valley. If you take search or commerce or whatever, some website would have provided some such service, and now they have enough data, they want to make the service different for different people. Okay? So the student will say, show me your algorithm you're using to build the original service. Presumably it was statistical. You took in data and you adjusted some knobs. And now I'll take specific data for specific individuals, and I'll do the same algorithm on an individualized basis. All right? And that'll require a lot of effort, a lot of work, and a lot of computer science, because I'm not going to serve just one model to everybody. I'll have to serve 100,000 different models, and that's a lot of work. But after a year or two and enough money, I could probably sort of do something like that. But then the boss adds some more requirements. The boss says, it should work well for everybody. I don't want to get too many dumb errors. All right? That sounds innocuous. But this system is probably a statistical one, probably developed with an error rate of 0.05 or 0.01 or whatever. And in a small scale, when you had maybe 10,000 people using your system, that means maybe 10 people are getting bad service. They're out in the tail somehow, and that's fine. Everyone will accept that. But from one day to the next in Silicon Valley, you went from 10,000 people to 10 million. Your service became popular. And if that same algorithm is being used, suddenly your 10 errors gets amplified into 10,000 people getting bad service. And that's hopeless. They will write to the newspaper. You will look awful. Your company will not succeed. That's a technical problem, partly. You have to worry about the tails of distributions, and you have to do a lot more statistics and a lot more thinking to make sure that you cover all those cases, that you don't have these bad cases. And in mathematical terms, it's the L infinity norm that we should care about and not the L1 or L2 norms. But we don't know how to do that. So my student sort of says, well, I can try. It'll be a lot of work, but I'm not sure my faculty ever taught me how to do that. But now it only gets worse. So those are kind of statistics meets system building. But now there's kind of the theoretical computer science that comes to play. The boss says something, again, very innocuous. Oh, by the way, whatever you build, it should run just as fast as our classic service. Again, this is critical in Silicon Valley. So when Google came out, you may remember if you were around in the 90s, suddenly you hit a return after you typed in your query, and an answer came back in 2 seconds. Before, you would hit a return, and it would take maybe 10 seconds, or it would be fairly random. And that was too slow for your work style. And Google was 2 seconds. All right, so now Google is planning to roll out a personalized search service. Much better, because it uses all this fine-grained data and everything. But behind the scenes, there's 100,000 models, and they're all going to be served from all around the world, and data's flowing and so on. So that's going to be slower, surely. But it can't be, is the point. Because if I hit the return and it takes 10 seconds again, I'm going to say, forget this. I don't like this new service. So they can't do that. All right, so now we have a runtime constraint on a statistical algorithm at scale. Okay, runtime constraints don't appear in statistics. All right, and computer science doesn't talk about the statistical side. It talks about runtime, but it doesn't talk about the risk, especially out in the tail. All right, so the student says, I just don't have any, I can build it and hope. And that's where we are with most systems that are called data science out there in the world today. You build and hope. All right? Now it only gets more interesting, and conceptually this next point is the one I find the most interesting. Again, innocuous statement. Oh, by the way, over the next 10 years, we're going to go from a terabyte of data to petabytes of data, and sure, that's good, right? Because you like data. The service will only get better because we have more detailed data about each individual. So it'll only get better, right? But of course, it can never slow down. That's the rules of the game. All right? So now you have a requirement, which is that as the amount of data scales, the runtime stays constant. Right? Well, we don't have algorithms like that. We don't have any theory like that. So now you have to hope, again, to build a big enough system with enough parallelism that, blah, 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 that it'll all kind of work. And it won't most of the time. So most companies that try to do things like this get down there somewhere and they fail. And Google maybe has enough money, they can, just money to death and get enough computers that it'll start to work, but it's a hope. So I like to think of this as where we were 3,000 years ago. Humans had learned how to build bridges and buildings, and that was really good. Economies were built and things went forward, but a lot of people died and a lot of tragedies happened. And eventually a field emerged. It was called civil engineering, where you were able to say, here's the sand, here's the wind, here's the river, and so on. Give me some guarantees that the structure you build won't fall down under certain conditions. Well, so I'd argue we have nothing like that because we can't solve any of these kind of problems. We have nothing like that for data science. Right, so we have a proto-field and a proto-engineering field. We have some mathematical concepts we're pulling from here and there and putting together in interesting ways, and we're showing we can build buildings and bridges. But they're not at all, it's not at all an engineering field. All right. And of course, it's not just engineering and technology. There's all kinds of other issues that come together when you interface data and humans and decisions. So the data is owned by somebody. There's privacy issues. I might want you to use my data, but pay me a little bit. I want an economic model for all of this. So all the fields, in fact, this is the first time in my whole career that every part of academia is interested in this. Okay? So in fact, I love that you're calling your institute data science, because that resonates around the entire university, the entire world. And I don't like the terminology AI. I think we don't have intelligence, so we're advertising something we don't have. And moreover, that's not of interest to everybody around campus, whereas data science is. Okay, so thanks for doing that. Okay, so I think that to get started on this, you have to sort of say, what do we mean by computational thinking, and re-investigate that, and what do we mean by inferential thinking, and put them together. So just to be a little bit clear about what you might mean by computational thinking, it's not just libraries of algorithms and a new language. It's modularity, it's abstraction, it's scalability, the core concepts you get in a good computer science curriculum. Less familiar, perhaps, to engineering-oriented people is inferential thinking. This is not just statisticians, it's information theorists and so on, and physicists. So it's always not just looking at the data, but where did the data come from? How did it arise? And it's an inverse problem of going from the observed data to the phenomena behind the data. Right? So the mathematics is that of inverse problems, whereas in computer science, it's pretty rare to see the inverse problems. There are some fields where you see it, but it's not as common. Okay? So putting them together is a challenge. If you look in the core statistical theory, which I think of as statistical decision theory, Bayesian or frequentist, you will see all kinds of trade-offs between various quantities: amount of data, risk, complexity, dimension, and so on. Little equations, d log n, d log d over square root of n, and so on. But you will never see a runtime in those equations. You can't trade off runtime for risk or for amount of data or for anything like that. All right, so the field just doesn't speak to this core set of issues. And it's not because it's trivial, it could have been done and no one just thought to do it. It's not trivial, okay, to put runtime into the statistical risk. And similarly on the computer science side, Turing theory and all of its branches talk about runtime, but they don't talk about statistical risk. You do not have an expectation over a loss inside of a supremum, okay? And it's hard. And in fact, you start to see this when you look at lower bounds. So lower bounds where you start to see, do I have fundamental understanding? And there are lower bounds in statistics. There's quite a few. They don't talk about runtime. Computer science, there's very few lower bounds. And most of the ones that exist are very far from the upper bounds. In statistics, they tend to match. And trying to take the lower bounds on the two sides and put them together is really, really hopeless. It just doesn't work. Okay, so essentially, I'm going to sort of get to this near the end, but I think that it's not Turing theory that we need. It's something else. Okay, so Turing led us to this point, but Turing's not the guy going forward. And in fact, optimization gives us at least a little more of a hint to go forward. Optimizations, maybe surprisingly, not just has algorithms and rates, but it has lower bounds. And those lower bounds are really interesting, and they start to look like they could cohere with statistics a lot better than classical computational theory. Anyway, new issues to be explored. So I'm going to change this outline, but I wanted to say a little bit about privacy, just because I think partly it's a medical community as well, and I know you're interested in those kind of issues, and show you a little bit of how to bring computation statistics together under the guise of privacy. I will skip communication, I don't have time, and I do want to say something about this last bit. It's recent research that brings together kind of the physics perspective as well as the statistics. Physics, I think, will always help us and guide us, and it is going to come up in this part of the talk. So let me say a little bit about this issue. I already alluded to it. Joint work with John Ducci and Martin Wainwright, colleagues at Berkeley. I think you know all of the, you can read that, but basically we know what the issue is. If I want your genome, I say, Renee, can you give me your genome? I'm studying some disease. And he says, well, what disease? And I say, something that runs in your family. And he might say, okay, give me your genome. And if I instead go to him and say, I want your genome because I want to set insurance rates. I want to see how many mutations there are of some kind in the population. And he says, well, that's socially useful, but protect me. Don't take my whole genome, subsample it or something. Or I might say, I want your genome so I can put advertisements on your website. And he'll say no. So he wants a knob that he can turn, which is the amount of privacy that I guarantee to him as I take his data. And that knob should be a continuous knob, and it should go from 0 to infinity. And it should be a real guarantee on privacy. And it should be as a function of the loss function that I'm using. What inferential problem am I studying? A disease, insurance, advertisements, okay? So we should have a dialogue. It's a market. And there should be a money value on that privacy. If I say, I want your genome to set insurance rates, and he says sort of, no, I say, well, if I give you $5 million, will you do it? He says, yeah. All right, so it's got financial value. All right, so we don't have that kind of market now. So how do you set this up? So first of all, just a couple of words about how computer scientists and statisticians think, to show you they don't think in the same way. So let's think like a database person for a moment. A query comes into a database, and out comes an answer, which I'm going to call, oddly, theta twiddle. So think of a banking situation, a classical database. It's got people in it, that's got their social security number, their age, and how much money they have in the bank, or whatever. And the query might be, who has the maximal amount of money, or something like that. So do we want to protect the privacy of people in the bank? Sure, we do. So there's several fields that have emerged. One of them is called differential privacy, where you put the data through a channel, noise it up, and now someone can look at the privatized database and can't say certain things about the original database. Like, for example, who was in the data. All right, so that theory exists, and you can prove things like, you put the same query into it, that theta hat is close to theta twiddle with high probability over Q, and over all queries and all over databases. That kind of theory exists. All right? And as that's being rolled out, I've leaned over the shoulder of colleagues that work on this and say, well, are you doing inferential things? And they say, well, the query, sure. The query could be, find the median. Isn't that the statistics? Or even do a regression. And they say, isn't that statistics? And I say, no, you're not getting it. That's just descriptive statistics. That's just taking the data in the database and describing it. That's not inferential. And they say, well, what are you talking about? And that's when I realized that I have a problem, which is they don't get inference. So I made this diagram, the following one, to try to give them a picture. So now let's think like a statistician, and let's change the model. It's not banking data anymore, it's medical data. So I've got a person, social security number, age, height, weight, and I got how long they lived if I gave them a treatment or a control, typical medical data. All right? Now, do I want to protect the privacy of the people in the data? Sure, of course. But am I interested only in the people that are in my data? Okay? In the banking case, probably so. I don't care about someone who's not in my bank, who could have been in my bank, but didn't end up in my bank. I don't care about them. But in the medical data, I'm definitely interested in people who could have been in my data set but weren't. Right? In fact, everybody in the data set could be dead and gone, but the data is still useful to me. It'll be used to give a treatment or not to someone who comes into my office tomorrow. That's the whole point of medical data. So that's inferential. I'm interested in people who could have been in my data but weren't. And that language right there, I guess it's a subjunctive tense, is inferential. All right? Could have been in the data but weren't. And that's not the way a database person thinks. They just think, here's who's in the data, period, and process it. All right? It's not just processing the data with algorithms and so on and getting out answers and hoping they're good. So what does a statistician do? They say behind the data there was a population, the people who could have been in the data but weren't. And it's not everybody, but it's some subset. And there was a sampling pattern that gave rise to them, and I have to be clear on that. And I have to solve the inverse problem such that I can put a query into the population, i.e. query someone who wasn't in the data but could have been, get out an answer, and prove that theta is close to theta twiddle with high probability over S and overall P and overall queries. So there are hundreds of thousands of papers and statistics that do exactly that. And there's probably tens of thousands in the computational literature that do the privacy thing. And there's probably 5 papers that put the two together. But that's exactly what's needed. Here's the picture. Here's what we should be doing research on. This is data science. You collect some data, all right, and you want to guarantee the privacy of the people for whom you collect the data. You gave them a contract, all right? But you don't care about the people in the database. You don't maybe care about them at all. They're dead and gone. You care about people that are going to emerge later. So I want to prove with high probability that theta is close to theta hat over Q, S, and overall queries and overall P. Okay, so I hope you can see that this is an example of a bigger problem. You put these things together, that's the real problem. All right? For want of time, in fact, let me just check. It's 9, 10, okay, I think I've got it in my head. For want of time, I won't get into, we've solved a version of this, a stylized version of this. There's a paper coming out in Journal of American Statistical Association, John, Martin, and myself, with commentary from various people. So that paper is already up on the JASA website. You can have a look. Let me just sort of say a little bit briefly. I'm going to flash some slides showing our setup here. This is kind of the standard picture of privacy. There's private data X1 through Xn. It goes through a channel, Z, and the statistician has access to only Z and not X. And what we're going to do now is there's a little bit of math, but this is a math group here, right? This is standard statistics. This is minimax. So minimum over supremum of what? This is a loss function of what you're trying to infer. This is your estimator. This is your loss. And this is a key to a statistician. You don't see this in computer science. This is the expectation over all the randomness, not just from an algorithm, but from the actual sampling pattern. Okay? So this is the maximum risk, and this is the mini-max risk. All right? So from the blue on, it's completely classical. And what you do in statistics is you study this mathematical object as a function of n, the dimension of theta, and all these other things, and you get out formulas like, you know, d log d over square root of n, and so on. Okay? So all we've done is add this new little green part, and what that is, it's an infimum over all channels which respect differential privacy to level alpha. So if you know what differential privacy is, you'll know what that means. Alpha is a constraint on the likelihood ratio. As I make alpha really, really near 0, I'm adding lots of noise. I'm giving myself lots of channels. And as alpha gets larger and larger and larger, less noise is added as a constrained set of channels. So this set of channels is fairly well defined, and we can do this infimum. Okay? We can actually do the math here. And we had to do kind of the same kind of math you do for minimax, but a little bit different. A few new ideas were needed, but not a lot. And we were able to get out equations from this solution of this. And we actually kind of got out one equation. I'm going to skip over a particular example. Here's the equation we got out, which is that if you had this in the original risk function, n appeared somewhere, 1 over square root of n, 1 over n to the 1/3 or whatever, you replace that n with n alpha squared over d. All right? So the alpha parameter is just multiplying n. All right? And this is interesting. Now we have a formula that has both some statistics and some computation in it. And this is what I would want. This is a little piece of engineering, if you will. So if I go to Rene and I say, I want your genome for some study I'm doing, and he says, well, tell me what your loss function is, and I tell him, and he says, well, for me, alpha 0.5 sounds about right. That gives me the right feeling of guarantee for that data set, or for that problem. And I say, fine, okay. So then I multiply alpha by itself, and I get 1/4, and I now know to get the same risk, I just have to have 4 times as many people as if people like Rene are giving me data as I would have had before. All right, and alpha can vary across the population. So that's something a person could use as a rule of thumb. They just take alpha, they square it, they multiply by the sample size, and they get the bigger sample size they need. Okay? So this happens not across just one problem, but across a whole range of problems, and it happens for information theoretic reasons. So we think of it as something of a law of private data analysis. And I didn't mention this n in the denominator, but this is bad. This means in high dimensions it's going to be very hard to achieve the differential privacy, and that's an example of the fact that differential privacy is probably too stringent. We kind of know that, but here's a quantitative evidence of it, and how you would like to try to get around differential privacy, still give guarantees, kind of is suggested by this formula. Okay, so it leads to mechanisms, but I'm going to skip that. Okay, so let me turn to the second half of the talk. So first of all, that approach actually generalizes to other classes of problems. We've done it for privacy here, but you can do infimum over other kinds of externalities. So we did this for compression, for example, and I'm skipping over that. But what if you say, I want to have a channel, because I have so much data, a huge amount of data, that I can't send it back to the central site for analysis. So I need to compress the data. So I have a channel that compresses it. All right? Now Shannon tells you how to compress that to get the smallest bit rate. All right, but what if I don't care about the bit weight? What if I care about using the data for statistical inference? So I don't want to just compress the data to get a small bit rate. I want to make sure the compressed data is still good for statistical inference. All right, so you want to do minimax and then take a further infimum over all channels that have a certain bit rate. And in that set of channels, one of them will be the Shannon one, but that'll probably be a bad one. It'll probably destroy the data for the purpose of the inference you have in mind. So you want to take it over all channels that have the inferential quantity you have in mind. And when you do that, you get a different Shannon theory that is inferential. So you brought together some information theory with statistics, and you get out compression schemes which are appropriate for keeping the data in the way you want for inference. And the mathematics is just the same as I just showed you. It's just another infimum over channels. All right, so you can keep going with this. You can do infimum over other kinds of constraints, but you can't do infimum over computation. All right, and that is the crux of the issue. Right? Because if you did an infimum over all computational mechanisms that have some resource constraint, that may be well defined by someone like Kolmogorov, but it's just not useful. It's too big of a set, it's too bulky, I can't do the mathematics on that. Okay? So I consider this still open and hard as to how to do things like that. The kind of the pure math approach would be to do something like that. And instead, many of us are just trying to hack around and find old ideas and use them in new ways. Venkat Chandrasekhar and I had a paper about 10 years ago now that took geometry as an intermediate between computation and statistics and got trade-offs between computation and statistics via geometry. So that worked beautifully, but only for a very limited class of problems, denoising problems. We also have had a line of work on using database ideas, concurrency control, to trade off parallelism against risk, but also fairly limited. I'm going to talk about optimization. That's been probably the most productive area. And then subsampling is also very, very active. If I have a huge data set, presumably I can subsample it and get algorithms that run faster. All right? But when I subsample, I probably get worse risk because my error bars will get bigger. Right? So how do I trade off the error bars against the runtime when I have parallelism or subsampling and other things like that? So there's a huge amount of work on this. It's completely heuristic. Those two papers are not so heuristic, but they're not also fully mathematically satisfying. So I'd say this is one of the important areas that take your computer science people who know about parallelism and subsampling and all that, but put them together with statistics. Make sure that they get control over the error bars and not just run an algorithm faster and show that it runs faster. Okay, so the last part of my talk, I will say something about one approach we've taken to try to get lower bounds on computation that are in some sense statistically relevant. But really this is a focus now on how do you talk about lower bounds in computation in some way in a generative sense. A lot of the lower bounds you see out there are mathematical existence statements. There exists some bad function. We want to go kind of beyond that. So let me acknowledge students of mine, Andrew Wibisono and Aisha Wilson, who have been working with me for several years at Berkeley on this whole area. And then Mike Betancourt has joined us in this last little phase on some of the recent work. He's a researcher at Columbia. Okay, so optimization I've already alluded to is a kind of a critical lingua franca. I think many of us who came up in the 80s thought that optimization was kind of a dead field that you just used its procedures. You use conjugate gradient or simplex or whatever. But it's amazingly alive now. And I think it's really a central place for many of us to work who have theoretical tendencies. Now, it supplies algorithms, certainly, but as I've alluded to, it also supplies lower bounds. It tells you what's the best you can do on a particular problem. And when you know that, that gives you deeper insight. It's not just some rate of some algorithm. All right, so it's not so known that it supplies lower bounds. If you pick up a classical book on optimization, huge tomes have been written, you'll see conjugate gradient, here's its rate. You'll see, LBFS, here's its rate, and so on. No lower bounds in sight. And it really was the Russian school, Nemirovsky, Nesterov, and others, who focused on lower bounds, and to their credit. So if you don't know about Arkady Nemirovsky, I think he's now 70 years old. There was a birthday party for him. He's now in Georgia Tech, and he's a leading, amazing figure on this whole Russian school, sort of opened this up. So many of us are following in their footsteps. Now, when you start to follow that field, you realize that, that it's actually an immature field. Actually, many open problems in optimization, especially when you start taking a point of view of data science. All right, so I'm going to say this in a different way, and it's going to sound a bit grandiose, but let it be grandiose, which is that there's this theorem called the fundamental theorem of calculus, my favorite theorem, which tells you how to go between integrals and derivatives. And huge branches of mathematics are that. In statistical mechanics, it's kind of the core idea in statistical mechanics is exactly a going back and forth between derivatives and integrals. So the most mature fields have done this a lot. They work on both sides of that. So physics, of course, has the Newtonian perspective that motion is given by F equals ma, which is a derivative. Okay, it's a differential equation. But then Lagrange came around and said, I can rewrite all that in terms of integrals of a Lagrangian, and get the equivalent physics. And of course, that has continued to this day. The energy perspectives have been dominant, but the differential equations are always there. Statistics has Laplace approximations, saddle point expansions, which have derivatives across saddle points give you information about integrals. So it's core in statistics. And then the numerical disciplines, finite elements is exactly about taking derivatives, partial derivatives, PDEs, and turning them into little pieces of integrals. And Monte Carlo, the best Monte Carlo methods, the hybrid Monte Carlo and so on, are trying to do integrals by computing derivatives, getting gradients. And I could go on. Many fields have something called the Herbst argument in probability, which is exactly the same notion. So optimization doesn't have this. If you pick up papers on optimization, there's only derivatives. You never will find an integral, maybe in a Taylor expansion. And so in that sense, I think it's still not entirely mature. Okay, so let's dig into this a little bit. Let's talk about unconstrained convex optimization just for simplicity. I also can talk about non-convex and constraints, but I'm not going to now. And here's just the great algorithm. Probably Newton knew about it certainly, but probably the Babylonians. You take the gradient at some point and you go downhill to update x. What's maybe not so well known is this has a convergence rate. Over the space of smooth convex functions, it converges at rate 1 over k. Right? Meaning that after k steps have gone down, the error the worst case error is of size 1 over k. Okay? So for a long time, that was just viewed as great. That's a good error rate, and it's useful and all that. But no one asked, is that the best you can do? All right? So to have a notion of best you can do, you need to have a lower bound. How do you get a lower bound? Well, you have to have a computational model. And if you say Turing complexity, then you can't say anything. The best you can do is to know the answer immediately and hop to it. So you have to have a constrained model. And so Nemirovsky and others came up with this. And they said, well, I'm going to allow you to see only function values and gradients. And I'm going to insist that your algorithm have its next value, its updated value, in the linear span of all the previous gradients. So that's a computational model. In that model, is there a lower bound? And it turned out there was. It's 1 over k squared. So it's faster than 1 over k. So that's interesting. So for a little while, there was an open problem. is there an algorithm that beats gradient descent? All right. And I wasn't around then, but I suppose the intuition was maybe no, because gradient descent is locally optimal. If you're just looking at gradients, it's the steepest descent direction. How can you beat that? And so it was kind of amazing when Nesterov wrote down this little algorithm here, which has rate 1 over k squared. And it's just 2 steps instead of 1. One of them is kind of a gradient step, and the other is kind of a little bit of a convex interpolation step. All right? So it's just a little algorithm, but amazingly, it goes faster than gradient descent. Also, it's not a descent method. It goes down and occasionally goes back up again. How can that be if you're trying to get down as fast as possible? All right, so a lot of mystery has come out of these equations. Nesterov himself doesn't explain them that well. He's just a brilliant guy who came up with them. So over the years after that, people took many, many classical methods and accelerated them. And this is a huge, huge contribution to the mathematical literature. And it's not as well known as it should be. But many practical algorithms are accelerated versions of classical methods using this kind of style of thinking. But there really isn't a generative approach to this. Here's a problem. Can you generate an algorithm just out of a set of principles? And so we've been working on this, and we have decided that the right way to think about this is you have to go into continuous time. All right? Because in discrete time, if you're hopping around a space, the notion of accelerating is just not so clear. Right? What does it mean to accelerate on a discrete set of points? Whereas in continuous time, it's totally clear. It's classical. All right. So for gradient descent, there is a sort of underlying continuous object. It's called gradient flow, hugely studied in mathematics, lots known about it. It has a convergence rate of 1 over t for convex functions, so it matches 1 over k, and so on. So the question is, what happens when you take Nesterov's equations and turn them into a differential equation? And this had already been done by Sue, Boyd, and Candace in a paper in 2014. You get this differential equation. So that's already interesting. It's second order, so you can expect some oscillations, damped thing. And they studied it and kind of understood the oscillations a bit, and progress had been made. Right? Well, we looked at this and sort of, I think, like Lagrange looked at F equals ma and said, but that's just some differential equation that came out of the air. Why this differential equation? What properties does it have? Are there other differential equations like that? For other frameworks, what's the appropriate differential equation, and so on. So to cut to the chase, we thought about this like Lagrange did. Is there an underlying variational or Lagrangian formulation which gives rise to not just that differential equation, but to all the differential equations that you get when you look at accelerated algorithms? All right, Renee, you want to tell me how much time I have so I decide exactly how to do this last bit? 5 minutes? All right. Sorry. Okay. So here it is. Here's the answer. This object right here is a Lagrangian. We call it the Bregman Lagrangian. It has a term right there which is called a Bregman divergence. I'll show you a picture of that if you haven't seen it. And it has the function f you're trying to go down on here. The alphas, betas, and gammas are just time scalings. They're not important. They just give you degrees of freedom to give you a family of algorithms and not just a single algorithm. Okay? So the core is that there is a Bregman divergence between where you are x and x plus x dot. So it has a little bit of a measuring a divergence in a kind of an elasticity notion or an energy notion. And this is really like a potential function. You're trying to go downhill on that. Okay? So let me go actually to this next slide. Here we go. Yeah. So here's the Bregman divergence. If you don't know it, it's just a classically studied in convex analysis. If you're trying to measure distance between x and y, you measure this vertical discrepancy using an auxiliary function h. That's the Bregman divergence between x and y. Okay? So we're taking a Bregman divergence between x and x plus x dot scaled appropriately. All right? Now, if h, this auxiliary function, this kind of reflects the local geometry. If that h is quadratic, then that Bregman divergence reduces to 1/2 x dot squared. So it's a kinetic energy. All right? So this is literally a Lagrangian at this point with some time varying. It's a time varying Lagrangian. Okay, so what do you do with Lagrangians? You do what Lagrange told you to do. You put them inside of an integral, and you try to find the optimal path that minimizes that action. And you can do that by taking a bunch of partial derivatives, and out pops a differential equation. And here is the differential equation that comes from that Lagrangian. It's a two-line proof. And so this differential equation, I claim, captures all of the known accelerated methods in continuous time. All right? So where does that buy you? Well, first of all, it captures all these methods. That's already pretty cool. But first thing it does is it actually gives you rates. And these rates tend to be the ones that match the oracle bounds in continuous time. All right? Here's the rate. Here's the proof of the rate. The rate is O of this time scaling function. And the proof is just you write down a Lyapunov function, you take its first derivative, you ask that that be negative, and this is true if and only if this is true. So a one-line proof of the rate for the entire family. That's already pretty interesting. But now, if you look at different rates, different beta choices of beta, what happens there is really very interesting. This Lagrangian is called covariant. And so what that means is that as I look at different rates, beta, in this family of scalings, that I always follow the same path, just at different speeds in continuous time. So that means that the path is critical, and the path is gotten by this Lagrangian. So that's a discovery. That's mathematics. All right? Now, the degree of freedom that you can move at any speed just means that in continuous time, you can go at any speed you want just by changing the notion of the clock. So if I'm using a certain clock and Renee uses a Chilean clock that goes faster, that's fine. All right? Or it goes slower in Chile. Yeah, okay. So fine. What if John uses a really fast clock? In England, they have exponentially fast clocks. Well, that's fine. He'll follow the same path. He thinks he's going super fast. All right? So in continuous time, that's all fine. All right? But now here's what's critical. When you try to go back to discrete time, the two fast clocks, you will fail to discretize that differential equation stably. All right. All right, so to do the mathematics of that, I had given this talk around the country, and a number of people came up to me and says, this sounds something like symplectic integrators. In fact, there's a particular person in the audience, I was at Princeton, who mentioned that, and some others did too. And I remember symplectic integrators from long ago when I was a professor at MIT. I took a class on this. Let me skip over this here. Okay, so here's actually a picture of, if you try to go too fast, in continuous time, that's fine. When you discretize it, it goes down to the optimum and then shoots off to infinity. It's unstable. You would never propose this as an algorithm. And you can't get a better algorithm. This was just Euler discretization. If you try Runge-Kutta or whatever, it's still unstable. So there's something mathematical fundamentally happening. All right. So we were posed, in my last 2 minutes, we were posing the following set of questions. Why can't we discretize the dynamics when we're using super fast clocks? All right, what happens when we arrive at a clock speed where you can start to discretize? Is there a mathematical sign of that phase transition? And then finally, once you arrive at that point, how do you actually discretize? Right? And we have now decided that the answers to these questions are found in studying what is called symplectic integration. Now, it doesn't answer all of our questions. It actually leaves you a little bit short of a full theory of optimization lower bounds, but it's progress. So symplectic integrators, if you don't know, were discovered, studied certainly by Jacobi, Hamilton, Poincaré, and others. It was a big area at the end of the 1800s. And it said things like this, that if you have a system of equations coming from physics or biology or whatever, you can solve them exactly. They probably conserve various quantities like energies and momentums or volumes in phase space in general, or exterior forms. And that fact is interesting if you're doing the physics. You want to conserve those quantities. But it also means there's kind of a global topology of these differential equations. There's some stability of them. And if you want to discretize them, you better respect that stability. All right? So in fact, if you discretize the equations of the cosmos, which are differential equations, you can get a discrete solution. If you don't do it to conserve energy, you're not doing the real physics. You're doing something approximate physics, and that makes no one's happy with that. So anyway, amazingly, these guys back in the 1800s figured out how to discretize differential equations so you exactly conserve volumes in phase space. And it's a beautiful area of mathematics. All right, and the consequence for us is that when they discovered that, their discretizations, you could move much more quickly than if you didn't do it their way. And that's the connection to acceleration. All right, so I'm out of time, so let me just show you a picture. So you have to go into the Hamiltonian perspective, and to get this, you do a Legendre transform, you have a Hamiltonian, it's time variant, so we handle that. And we set up this symplectic integrator, and here's a picture of this happening in real life. This is a particular function. This is the integrator. You can see it's not a descent method. It goes down, then it oscillates, it comes back up. So it's like a car going on the highway. It goes really fast, so it swerves. All right? And this rate right here is exactly the oracle rate. So it is achieving, as promised, the oracle rate. All right? And then the last little part, 30 seconds, is that if you now compare this to Nesterov on this function and many others does exactly the same thing. He achieves the oracle rate as guaranteed, but in this kind of more ad hoc way, if you will. We don't really understand it. But at the end, he actually does a little better. So his thing has a little bit of magic in it, which is that if you have a lot of momentum far from the optimum, that's good to get downhill fast. But near the optimum, you want to damp down that momentum more quickly than a symplectic integrator does. Okay, so there's a little bit of magic there. On the other hand, he needs 2 gradient evaluations per iteration. We need only 1. So our curve is actually 3 times faster than his in clock time. All right, but that's now a mathematical mystery, is how do you get a Hamiltonian perspective that captures this fact about Nesterov, which he bleeds away momentum at the end and actually dives into the answer. So that's kind of a fact that's different about physics and optimization, which I think we still don't know how to talk about. So we have an ad hoc approach to that, where we're actually able to do it by adding a gradient flow term to a thing, but I'm going to skip that. Okay, so let me hop back to the very top level. I hope you got the big message here, which is that it's not just about the data and the building of systems that do that. There's a huge number of conceptual problems that we need to face, both because they're interesting and mathematically challenging and so on, but also if we don't face them, we're not going to build systems which are actually have any guarantees. There's going to be systems that people are hoping are working. So to me, this field is actually not mature at all. It's not really achieved that much yet. It's just at the very, very beginning. So having an institute is exactly the right thing to do, and especially for the young people in the audience, learn about deep nets and all that and implement them, but don't just be empirical. This is a mathematical field, and take the mathematics seriously. Thank you very much.